All right, well, I appreciate you guys joining us today. Today I have the opportunity to talk about a really unique project that I've been very fortunate to be a part of. It's actually one of the most exciting things that I've ever been a part of in my entire career so far. And it has the potential to have a massive impact on the way that we do computational science, engineering, design, and everything that we use in society ends up having some sort of way of being touched by this type of modeling. And the accelerations that we're getting in partnership with Cerebras here are just amazing. So when we talk about the current state of climate and the United States and where we're at with the administration goals, we're really at facing a once-in-a-lifetime need, right? The president has outlined goals that are as ambitious as the space program, and as ambitious as the space program that was, the generation from my father. And we're actually faced now with a once-in-a-lifetime solution that could help us actually meet those goals, just like we were with the start of NASA here. As I mentioned, the administration has set forth some really ambitious targets. And by 2030, we hope to have a 50% emissions reduction on the grid. 2035, 100% clean carbon-free emissions on the grid, and by 2050, we want to have a net zero carbon economy. And when you state it as just 3 goals, those things sound achievable and easy. However, the amount of design and engineering that has to happen in the time frame that it has to happen in to meet these goals is incredible. We're talking about developing completely new technologies that don't exist yet, deploying them at large scales, with capital in the multiple billions to trillions of dollars in order to convert the economy the way that we have to do that. And that all has to happen in 15 years. It's a really ambitious goal. And one of the big things that we face, the challenges that we face is computational modeling. We start all of these ideas as ideas that are based on scientific models. We write those things down, and then we develop computational models to try and get uncertainty quantification, to try and get design optimizations before we actually go and spend a whole lot of money building something. This is something in my father's generation that they would just have to do experimentally. But now with the advent of supercomputing, that the pace of that kind of development has really increased, and now we're faced with the ability to do this kind of modeling in what used to take months to years to do, we can now do in an afternoon or a few hours. So really, Netl and Cerebras right now are at the forefront of this new technology wave that's coming through, and I'll discuss what makes the difference here in a minute. As I mentioned, we have once-in-a-lifetime need with carbon sequestration, net zero carbon economies, with all kinds of physical equipment that we need to design. And we've come up with a solution on the Wafer-Scale engine that allows us to model these things not tens, not even hundreds, but nearly 500 times faster than what we could do on the largest supercomputers that DOE owns. And not only that, we are able to do this with energy consumption that is estimated to be between several hundred to in the low thousands of times less energy intensity per unit compute. So let's talk a little bit about what makes that so. For our comparison, when we did our studies, we own the Joule supercomputer on the Netl Morgantown campus, and what we're looking at is a massive change in size. If we look at the changes that are happening in size, we haven't seen this kind of change in compute density since the transition from vacuum tubes to transistors in computer history. And so we're going from something that is the size of a building that has something on the order of 5 petaflops of performance to something that's smaller than your home refrigerator, and it's more, well, it's in the box over there. It's more akin to the size of a dorm room refrigerator. And the weight savings. You know, we're going from the size and weight of a house to something that's the size and weight of maybe a dorm room refrigerator with more beer in it that you could possibly imagine. But anyway, so the change in scale is really, really important for achieving the speed and the energy efficiency, and we'll talk about that in a little bit. So as I mentioned, I think that this is one of the largest changes in size in computing since the transition from vacuum tubes to transistors. And you know, you can go around at supercomputing here and you'll find all kinds of blades, okay? They're gonna be 19 inches wide, a rack wide. They're gonna be anywhere from 2 to 5 inches tall and about 24 inches deep, okay? And inside of this stuff, we have a processor, a group of memory, and a network interface card, okay? But all of this stuff is separated by inches to feet, and that the paths that the electrons have to travel on are really large in that respect. What Cerebras has done is essentially stripped out all of the stuff that's not necessary for numeric computation and shrunk it down into a tile where the dimensions on this are about the size of a thickness of maybe 2 sheets of paper in width and height. So we have the same components. We have a memory, we have a processor, and we have a network interface that allows us to talk to neighboring tiles. And the size reduction is really important because it dominates how much energy it takes us to move data around. And when I talk about we have to move data, it's an incredible amount of data. When we run our scientific simulations, we're moving as much data as between 7 and 20 times the entire world's internet traffic, and that's all happening on this thing, okay? The amount of data movement is huge for these type of problems, very data intense problems to solve. And as I said, the miniaturization is extremely important. That big computer that we have at Netl, this is a megawatt class substation. Cost us a couple $1 million to put in. And that was just needed to feed that large supercomputer. This breaker right here is well, I wanted to get it relabeled to be a 120 amp breaker, but that's all that's needed to run the Wafer-Scale engine to get the same flop performance that we are getting on the Netl supercomputer. So the energy savings is incredible. The infrastructure savings is incredible. The cost savings per unit compute is incredible. Orders of magnitude difference. And so talk about energy savings, well, that really translates to CO2 savings. Netl was involved in the DOE Net Zero Lab initiative, where we are trying to reduce our carbon footprint of every lab. And what we found was computing, our computing resources accounted for over 50% of all of the lab's carbon emissions, just because it's so power hungry. And a lot of that has to do with the size. So miniaturization is key. And we estimated that we could save about 50% of our total site emissions if we would transition at the same amount of work that we do currently on Joule. If we could transition just 50% of the workload that we do on Joule over to doing it on the Wafer-Scale engine through this type of interface, we would reduce the projected emissions by, I think this is 2028, by a whopping 30%. This is the largest and least expensive single source point source reduction that Netl can make in our estimation. Not only that, the efficiency is so good that for the first time we can actually really practically consider a net zero computing. We estimated that if we were to power this via solar with battery backup, we would need something on the order of 100 homes, which isn't really all that large of a solar field, especially when you compare trying to power 24 kilowatts of power against 1 megawatt. I mean, the solar field would be needed to power 1 megawatt sustainably in a renewable fashion would be many, many times the expense that Joule costs. and here it's actually less than the cost of the purchase here. So that's one thing that I find really fascinating, that we might be able to actually achieve a net zero, not just lower carbon emissions, but net zero computing. So what is Netl doing? I mean, Cerebras was great. They developed this great thing. They did a lot of magic, actually. Well, it seems like magic, to get this chip functioning and not tearing itself to pieces and cracking and all kinds of stuff. That was a major challenge, right? You guys overcame all of that, right? Yes, you did. It works. It runs. I know it works because I've run it. So anyway, what Netl is doing is developing an interface for modeling. We call this the Wafer-Scale Engine Field Equation Application Programming Interface. And it's really a domain-specific language that is meant to solve stencil problems, scientific models, to model the processes that we have around us. Heat transfer, fluid transfer, molecular dynamics, those kinds of problems are all types of field equation models, okay? And we think that this is a killer app that's going to help propel the technology forward, and we believe very strongly in making this happen. So what kind of things do we model? What does it touch, right? It touches everything from household goods, like modeling and designing a refrigerator. Here we see a variety. Like I mentioned, we do everything computationally now ahead of time, so we have a bunch of different heating coil configurations that something like a company like Whirlpool or would model, right? These kind of things are field equation models. You're modeling the temperature heat equations, and probably doing a couple fluid dynamics with that. Of course, automotive industry is huge. I mean, everybody cares about fuel economy in their cars, or I guess electron economy if you're getting an electron car. And at the highway speeds, the major dissipation energy is aerodynamic drag, right? Of course, weather forecasting. This was Hurricane Ian, or what was it? Yeah, Ian, that came through, and that again is all coupled types of computational fluid dynamics.
So you said if you moved 50% of the workloads at Netl over there, do they fall within these categories, or is it much broader?
So Netl is focused primarily on a couple of workloads: computational fluid dynamics for design of energy conversion systems, and molecular dynamics. So if we move those kind of workloads over to the WFA, we would make a significant impact on what we're able to do here.
And that's the 50%.
That's roughly what we think. Yep. So Netl, as I mentioned, we do a lot of computational fluid dynamics. We do a lot of novel equipment modeling, which is all CFD based with mass and momentum transfer. We also do underground modeling of reservoir modeling, which is also very similar to CFD, and we of course do a lot of molecular dynamics and density functional theory. And the WFA is capable of capturing all of these types of things within its framework, and able to port that kind of code directly to the Wafer-Scale engine. So that's what Netl is trying to get done. So this is the first demonstration that we had of the WFA. We solved the heat equation in a block at multiple billion cells resolution. And we compared it against the same code that we wrote in OpenFOAM, running on Netl's Joule 2 supercomputer. And we were able to achieve scaling, strong scaling that was incredible. The majority of time that we spend in doing iterations on a supercomputer is spent because we have such poor network bandwidth and latencies. And so that really impedes the speed that we can reach a solution. The WFA has, or the WSC has some unique properties that allow us to strong scale down to just 50 cells before we start to notice overhead. Unbelievably small amount of work per processor. And it's not that we see bandwidth or latency limitations. It's the fact that we have to set vector addresses, vector links, and those kind of things. That is the overhead that we start to see impede that. So the incredible result was that we were able to achieve over a 470x improvement in speed over traditional supercomputing with these type of problems. And not only that, we did it with a very simple Python interface. This program's almost exactly like NumPy. And so we see this is the explicit formulation for the heat equation, and we did that just as a demo. We can do much larger pieces of code. We set up the interface so that we can handle virtually an unlimited size of program, because we can stream the data right onto the chip, the program code right onto the chip, and make it run at these kind of speeds. So what do we do in short term? Well, we have access via Cerebras that's providing, has been providing access to the hardware, at least in this study. And we were just awarded time on NeoCortex, which is run by NSF via the Pittsburgh Supercomputing Center. And so we're starting to transition. Netl is running our own codes now on that machine and bringing that environment up. And we're bringing more user support towards the NeoCortex environment, so that we can have a single unified container environment that allows you to run on the Wafer-Scale engine with just one command line launch in Python. Longer term, we're looking into exploring purchasing of our own Wafer-Scale engine, hopefully through some funding that would be coming through the bipartisan infrastructure law, and getting a system at Netl so that we can develop at a much quicker pace and begin to explore partnerships with external partners like Ansys and other software vendors to build an interface to the Wafer-Scale engine. So when we look at potential partnerships, we have stuff going on with NCAR. We've been helping them evaluate the WFA for weather modeling. They're also running on NeoCortex. And we've also been talking to other potential interested parties that could accelerate their existing software through the WFA on the WSE. In particular, we've been talking with Ansys, and of course we have our own code, MFix, that we've been working with. And so what is that really going to look like? So we have an equation modeling interface, the domain-specific language in the WFA, that is able to compile an executable that runs directly on the Wafer-Scale engine. And so what we're proposing developing with other interested parties is a way to communicate between their existing software and the WFA, so that we can port the equation sets directly into the WFA and onto the wafer. And so we're looking at developing communication layers, input management layers, the ability to save files and restart checkpoints and those kind of things are the activities that we're looking at. Yeah. And so there's nothing, as far as the government is concerned, that's specific about Ansys. We're willing to work with any partner until somebody buys the rights and technology to something. But Ansys happens to be one of the largest software vendors in the world, and a close partner and a long history with Netl. And so we're talking with them to try and figure out how we can make this happen, and trying to secure funding to make that go as a first case example. So in the short term, we are actually developing a finite volume CFD capability in the WFA. We're also looking and exploring how we can integrate this with other software platforms like MFix and Ansys Fluent. Also, there was a lot of interest I think at Ansys for doing automotive modeling through LS-DYNA. That's another big platform and a product that they offer that could be accelerated that way. Longer term, we're looking at doing geodynamics, molecular dynamics, geomechanics, and structural dynamics. These are all fields that Netl is involved in, but it's going to take some more manpower in order to do that, and some domain-specific experts that we can train in the WFA to start writing code that would be suitable for these applications.
Is there one of those that seems like to be rising to the top to be a next target?
Well, yeah, actually, geomechanics is really easy. because it's typically structured grid, which is something that we already do, and we have a lot of experts there. But we're also looking at doing molecular dynamics modeling. In particular, we're looking at, I have someone that's interested in doing the icing model, which is magnetic domain consolidation. And so that looks like it's a fairly straightforward port, and we should be able actually, they're looking at maybe wanting to do 2D, and we should be able to do thousands of icing model runs at once through the WFA, running in rows on the Wafer-Scale engine, one row per simulation. And so we should be able to get a huge statistical advantage in the ability to do molecular dynamics. And from there, we would start looking at doing density functional theory, which is kind of the next step. And then I think in future generations of the WSE, we'll have more memory available to us. And if that's the case, then we can look at, and actually we can trade memory for bandwidth. So if we get more bandwidth off chip or have more memory on chip, we can look at doing Eulerian-Lagrangian type models, which is what the typical molecular dynamics stuff will do. So the future is pretty bright there. So I wanted to give you a little preview. We actually have this model running in simulator and in our validation software. And this is a lava lamp simulation, and the resolution is low because we can't afford to do a whole lot of resolution. It takes a day to run this simulation at the resolution that we're running at. But we are testing this model now on the Wafer-Scale engine at NeoCortex. We just got through some hardware debugging right now, and we're doing some software debugging to get this to run. I was really hoping to have an image to show you guys of the first multi-100 million cell fluid dynamics simulation, but it just didn't work out in the amount of time that we had to get ready. But we expect any time in the next few days to week to be able to have that. I was debugging this 20 minutes ago with one of my colleagues, running tests to try and figure out where we're having some issues. So when we get that done, we'll have an announcement on that, and you can watch NETL's and Cerebras' page, but it's coming in the next couple of weeks. And from here, we're gonna start moving towards unstructured mesh problems, I think. That seems to be of a high interest to industrial partners. The world is unstructured, right? So if we can gain a lot of speed by doing structured problems because we don't have two memory lookups to get a value, but the complexity of the world demands that we do that. So I think that's going to be the next direction that we head. So I'm really excited about it. Again, this is one of the most exciting things that I've ever been part of. I'm not a computer scientist. I've never been trained as a computer scientist. Everything that I've learned about artificial intelligence, computer science, and modeling, I've taught myself. And you know who else was like this? John von Neumann. He was a chemical engineer as well. And so I tend to think very out of the box, which is maybe why I was attracted to this and saw the potential. And actually there's a number of things that I think we do in computer science in supercomputing that are really quite silly as far as how we could improve the speed. And I think, in a partnership with Cerebras, forward-thinking people who are willing to take risks and make something happen to change the world, I think that's the right kind of environment to be in. So it's been one of the best partnerships I've ever been a part of, and I've been really, really happy to be working with this. So I think with that, I'll conclude and take any questions.